So good morning, everyone. Today we're going to start our last but not least key speaker section. And today we will have two key speakers.
1 second.
So one of them is Bożena Smerejak. I hope I pronounced well. And the second we have Katerina Brewer. She now is in our room. Yeah. So let me invite Dr. Bożena Smerejak she is the professor at the Institute of Soil Science and Plant Cultivation, and she's State Research Institute, Poland. And today she's going to talk about soil monitoring systems in Europe. Why are they important?
Good morning, everyone. I hope it works properly. No.
Now it's working.
Probably now it works properly. Thank you very much for nice presentation, and thank you very much the organizers for inviting me. Not to talk about engineering, but to talk about problems, natural problems we have to face in Europe and also around the world. I would like to put your attention and a little bit tell more about soil monitoring systems in Europe and why they are important. I am the professor in the Institute of Soil Science and Plant Cultivation, a State Research Institute and Department of Soil Science, Erosion and Land Protection. And for many years, I was involved in different monitoring programs carried on in my country. A little bit about the history, what was really very important and what was the basement of soil protection. In 17th of the last century, the European Soil Charter was delivered, and in this charter we know some sentences from it that soil should be protected, that soils are developing very slowly, and so on. And almost 10 years after, the World Soil Charter was published, was delivered, and adopted in 1981. And from those years, many initiatives started around the world just to map and also monitor soil properties, because that days we didn't know a lot about soil properties. Only some countries did implemented some programs just to know soil properties, usually for agriculture, because it was very important for soil management practices. And in 2015, the International Year of Soils put soil back on the international policy agenda, and also soil issues were implemented into a United Nations sustainable goals, and therefore more attention also were paid on soil properties. But we don't want now to know just properties. We need put more attention on soil protection and soil health, because we implemented in Europe, European soil deal. And in this strategy, some new definitions were implemented, like soil health, soil ecosystem services, because soil functions and such issues were known from 2006, where the first soil strategy were adopted in Europe. Monitoring of soil properties are very important to observe and check the progress or regress of soil quality over a period of time, and keep under systematic review. Those are programs which are in different countries implemented over a period of time, and only assessment or evaluation of actual situation are not considered as a monitoring program. It should be the systematic review, and as it is defined elsewhere in the literature, soil quality cannot be measured directly, like our health, because usually we did a lot of parameters. We investigate different parameters of our blood, for example, to just to know whether we are healthy or not. And the same is for soils. They cannot be measured. The soil quality is not measured directly, but it is assessed using different indicators referring to soil physical, chemical, and biological components. Therefore, in monitoring programs and the assessment of the actual states of soils, many indicators are implemented. Many indicators are implemented to assess the function of soils and the soil as a cool system. I would like just to tell you a little bit about our country level monitoring programs, because Poland is a country where agricultural soils consist of almost half of our territory, and we have to monitor quality of those soils, because it is important for our farmers and for our agriculture. Almost every country in Europe knows the quality of soils and soil cover and typology of soils. The same is for my country. We know from previous monitoring programs that we have sandy soils over half of soils devoted to rural agriculture is developed from sands. So the first layer of the soils are developed from sands, and therefore our soils are very specific, and they have very low content of organic matter, and because they have also very low content of clay, and moreover some sands are deposited on loams, and therefore some soils are also they have susceptibility of compaction, and we have counted on our based on our monitoring results that almost 26% of Polish soils can indicate susceptibility to compaction. Of course, based on results of monitoring programs, we have the raw data, but we can apply them for modeling. And some of those results become, and some of those maps were based on real data, and some of them the data were used for modeling and for interpretation of or interpolation of the data to for the next for other territory of for other for regions, and just to have the map of our territory. Based on monitoring results, we also know that our soils can be touched by potential water erosion and actual water erosion. Actual water erosion can be is dedicated to or about 7% of our soils are impacted by soil erosion. What about contamination? In Poland, we have very many monitoring programs related to for example, monitoring of the quality of air, of water, of sediments. But in this presentation, I should focus on mainly on soils. But one of the national monitoring program, part of national monitoring program, is also soil contamination. From 1995, we have implemented a monitoring program where in 216 control points, we monitor contamination of our soils, but also the quality of them. This monitoring program is dedicated to arable soils and the upper layer of them. So we know the situation related to organic compounds and also trace elements, as well as organic chlorinated pesticides, PCBs, non-chlorinated pesticides, and so on. And those points were located according to soil properties, industrialization, population density, contribution of agricultural land to the total area. And thanks to this monitoring, we implemented in our law the acceptable levels, thresholds for different organic compounds. So the current status of soils are that we have about 2% of soils which can be said that are polluted with, for example, trace elements or other organic pollutants. And those soils are concentrated especially in industrialized regions of Poland. This situation is common for different countries, and it is not very specific for my country. But those data is public available, so everyone can see the concentration of different pollutants in our soils. But also as you know, because in Lithuania, a common agricultural policy is also obliged because European Union, also your country, is paying for different scenarios and different actions implemented by farmers. And also in Poland, 8 years ago, was established next monitoring program. We have them about 10 or 12 related to different kind of pollution, and it was aimed at the comprehensive evaluation of common agricultural policy impact on soil parameters. It means does the common agricultural policy really positively influence soil parameters? Because a lot of actions related to Pillar 2 and subsidies were related to the improvement of soil quality. So we dedicated this monitoring program to different kind of payments, including sustainable agriculture, soil and water conservation, valuable habits under nature, 2000 areas, organic farming, less favorite areas, and it was many parameters. And also it was dedicated to soil type and texture, farms area, and also regional diversity in farming conditions. We had to do this because we are working for the Ministry of Agriculture and Rural Development. We are the institute working for this ministry, and partly we are working for Ministry of Environment. Therefore, we selected different farms and also implemented this monitoring program, where we have this period for a period of time after which we continue assessment of soil properties. It's 4 years. We have about 16,000 of points for this evaluation. It is not in the grid like a common grid, but it is much more related to different farming to different common agricultural policy evaluations. And we established this monitoring system on country level and farms, and measure different parameters. After the first evaluation of soil properties, very specific evaluation of properties, was held in 1992, and then we knew that almost 78% of our soils indicate acidic character. And after several years, we also prepared the second map and knew that the situation was not changed. And based on those data, using the very modern tools like machine learning, we also evaluated some properties. And we know that the main factor which is really affecting the agricultural production in Poland is acidity. We knew it, but we confirm it based on monitoring results and also mathematical models and artificial intelligence and new techniques just to confirm those facts. And why this results influence really what those results and this information, is it really important for the agriculture? It is, because based on that, because based on regional distribution of and situation with acidity, we can evaluate, for example, losses of macronutrients from soils, and then we can better implement the better management of our soils. Based on this monitoring program, we can evaluate status of agrochemical soils. We can calculate carbon stock in agricultural soils. We know that even if we really want to implement the best management practices, our soils are too weak to sequester a lot of organic carbon. It will be the mineralization will occur very fast. But thanks to the data and databases, we can also participate in joint European project. It is EGP Soil. I will tell a little bit more about this, although I have only 5 or 7 minutes. It is dedicated when we started, and your institute, I know that colleagues from Lithuania are also involved in this project. When we started it, we didn't know about new soil strategy, about healthy soils, about new soil health law. And so many initiatives were started during the realization of this project. Even European Soil Observatory was established and announced that it will be institution which will somehow provide information and store information, and it will be something different comparing to European Soil Data Center, SDAC, belonging to Joint Research Center. So we have a lot of laws and a lot of different acts where the soil quality is really implemented very strongly. And I would like to tell also about monitoring of soil properties, but based on example of EGP soil project. One of this work package of this project is supporting harmonized soil information and reporting. It is nothing new, because SDAC was organized to do this. Different institutions, different organizations like Global Soil Partnership, FAO, they are involved in such actions. For example, to harmonize the data, to harmonize methods for determination of chemical, physical, biological properties, but still there is no effect. There is no really visible effect of those organizations' activity. Therefore, in this European soil project, the ministries are Ministry of Agriculture, of Environment, and also other political bodies are involved in the project. and they have to pay partly to be involved in this project. So what now we are doing, it will be probably implemented in the upcoming political activity of European Union, because one of expected impact of this project is to elaborate the roadmap for European policy beyond EGP for the next 10 years. Therefore, it is very important. And the other very important purpose of this project is to prepare the program and also the cookbook, how to prepare soil data, how to upload them, how to share them, and how to stream them to European Soil Observatory. It will be the final product of this project. Moreover, this project has also the internal project. It is a big activity. And in some of those projects, as you know, now the indicators are very important, which should be selected just to properly evaluate soil health. And therefore, some part of our co-workers in CYSENi or Minotaur projects are working for that. But the first action of this project was to evaluate the current situation of data in EGP partners. We have in the consortium of EGP, we have 26 partners from 23 countries around Europe. Those are not only European member states, but also other countries. And it is very interesting to see that we have a lot of data. We paid a lot of money. Each country spent a lot of money on monitoring programs, which had different purposes and were focused on different issues. So we have a lot of data, but a lot of data on soil texture, for example, soil acidity, electrical conductivity, but those data are different among pedoclimatic zones of Europe. Therefore, indicators of soil quality and soil health can be different for different pedoclimatic zones. And in monitoring programs, there are gaps. There are gaps, for example, on cropping systems, on management practices, and so on. What we really need to monitor in Europe, management system, which result in, for example, soil carbon sequestration, improvement of soil quality, increasing the water holding capacity, and so on, because we know each parameters that can influence, but which management system really compensate all of those properties and really influence to make soil quality, better soil quality, and also fulfill the requirements of European Green Deal. And what is really also important, and what was also pointed out by other initiatives, we use completely different methods. Therefore, sometimes it is impossible to compare our data, national data, with among countries, even in neighboring countries. So we have to do something more, even if we have a carbon. Some countries measured only carbon concentration. Other ones can measure, for example, carbon by wet combustion, dry combustion, and then what we really need now, it is not concentration. It is the pool of carbon in 0.30 centimeters of soils. Many monitoring programs were dedicated to the upper layer of 0.20 centimeters. So we have to recalculate our data and implement pedo transfer functions. So it is almost. I have only a few samples, and if you want to see, we also, if we implement even measure of acidity, we have different analytical methods in water, in calcium chloride, in for example, potassium chloride. They are not adequate to each other. And available data, what we really we have to face, what problems? Wide variety of formats and standards, lack of communication, coordination between different organizations. Even in my country, Ministry of Environment has its own monitoring program, and Ministry of Agriculture own program. And this is the same situation in Europe, believe me. And some countries like Portugal doesn't have even any monitoring program, and they don't know exactly the properties of soils. But the only, and also we think that data availability is a very common situation, that it belongs to the government and can be shared and download very easily. No, some data belongs to governments and in Europe, and also private organizations. They don't want to share the data because some of data are sensitive. For example, contamination. Contamination means the next remediation. Remediation can cost a lot, really, and this is very sensitive data. And so, what about how to compare national data and how to make them useful, and how to solve this problem. We have in Europe Lucas, Land Use and Coverage Area Frame Survey, belonging to the it was under the SDAC, this Lucas program, and then countries under this EGP soil program did double samples. So the samples collected by surveyors of Lucas were divided into two portions, and one portion was sent to GRC laboratory and other one to the national laboratory. And thanks to that, these factors and pedo transfer functions can be established. Why soil monitoring systems are important? proper management of soil in each member states and in the whole European Union. Although we don't have the same problems and the same properties of soils. Evaluation of soil functions and ecosystem services, because although we have implemented soil strategy in 2006, still member states did very little for soil protection. And therefore, now we have ecosystem services, soil health, and other definitions which we have to face. Reporting to European Soil Observatory and national political bodies, because we even if we introduce some programs, for example, common agriculture policy, we will be evaluated. As you see, not properties, but among different factors we can mention for CAP evaluation, they were not dedicated to soil properties. Probably we will they will be implemented. And of course, evaluation of efficiency of implemented political tools. If you want to reach some limits till 2030 and 2050, we have to have the tool to evaluate it, just to check it. Thank you for your attention. And if you would like to ask me question, I can answer now or in the foyer. So it depends on you.
Jana, for your nice presentation. So now it's time for the questions. Do you have any question? Yeah.
Hello.
Thank you very much for such an informative study. I have basically two questions related to the soil contamination. As you mentioned that there is a specific threshold level for like some trace elements that you declare to have like to declare the soil as a contaminated. My first question is that do you have like studies? What are the reasons for such contamination in the soil? Are there like the localities of the industries or something like this? Or normal agriculture land can be contaminated with such a trace element? And another question is related to this also. That is, if you declare some soil as a contaminated, do this law have some like follow-up so that no agriculture crop or some edible crop should be grown in that contaminated soil or not?
Okay, I would like first answer first question. What about anomalies in concentration of example heavy metals? Some of them, of course, due to industry and mining and also metallurgy and also spread of contaminants, you know, on neighborhood areas. This is the first, and the second is the natural high concentration of heavy metals, but we don't indicate it as a contamination or pollution because it is just normal. And what about the law? We have certain amounts of certain thresholds for heavy metals and other contaminants into in Polish law. Into layers, I mean 0.25 and 25 1 meter, and but also the regulation. In the regulation, it is mentioned that even if the total concentration is very high, also risk assessment can be implemented. It means that we can also mention bioavailable fraction of contaminants. If it is very low, it means that no other actions like remediation can be implemented. But if there is high risk of, for example, migration of contaminants to plants, for example, or animals, in the old our rules, we had also some recommendation for agriculture. Then in such areas where the concentration of zinc, nickel, or copper is high, farmers are allowed to grow only ornamental plants or trees, but nothing to be used by humans or animals. Only just for other kinds of production.
Thank you so much. I have one question. What all of us should do for to improve soil quality, like not like research, but like citizens? What all of us should do?
Yes, it is very strong, very strong attention put on the public activity towards soil protection. So, of course, the how to say, the public voice really is very strong, and public opinion can create the future and create the present time. And if we want, for example, we don't pay our farmers for growing, we pay them for the food, but mostly for soil protection. If we want them not to use pesticides, herbicides, and use more natural, natural pesticides and other protection substances, they will. If we want, for example, prevent our soils from erosion, and we really want to say farmers that we really want to have such systems, maybe our voices will not be heard. We can only partly then influence, because there is also tradition. We have to change our traditional soil use in some cases. In some cases, we can implement very fast changes, but in some, we have to wait for the results for longer time.
Okay, thank you so much. And we have some small presents for you,
Oh,
for
thank
your
you.
work, for this nice presentation. So thank you so much.
Thank you. Thank you so much. Very nice. Thank you. Thank you.
And now I would like to invite our second key speaker, and she is Dr. Katerina Brewer, from Associate Professor at the Department of Chemical and Materials Engineering at New Mexico State University. And today she's going to talk about engineering co-production to support sustainable agriculture.
Labasritas, ponai iponios. Achu ush kvietima, dalivatu yushus. Conferencioia CYSENi, du tongstanchi, dvideshimt tris. Good morning, ladies and gentlemen. Now that the hard part of my presentation is over, I this morning would like to talk to you about something that is in between many of your areas of study. So I know in my audience, I have several people who do agriculture. May I see those who do agriculture? May I see your hands? And I know we have some people who do engineering. May I see the engineers? Now, do we have a few? I know there are also some physicists. We love you too. Do we have any physicists or chemists present? Yay, we got some. Okay. What I'm going to talk to you about today is the areas where all of those things meet together. And this is what my group does. And this is how to engineer co-products. So not the primary products, but the other products to make sustainable agriculture work. So I work in chemical and materials engineering, but most of my research is in agriculture, which very much confuses our administration. First, like every faculty member, I have to thank the people who do the real work. And these are the students in my group. For those of you from LAMPS, you may recognize a face in this photo. This is Mohammed Ayaz. He came to join my group last October through this January to do some research. So a little bit about where I come from. How many of you have met someone from the States? Okay. How many of you have met someone from New Mexico? How many of you knew there was a state called New Mexico? Okay. There are some Americans who still get confused, but anyway. So I want to give you a little bit of information about what my group does and some examples of how this work is applicable in the Southwestern US. So we'll talk about what engineering biomass co-products means, talk about some new bio-based insect repellents, talk about hydrothermal liquefaction, a little bit about hemp, a little bit about biochar and how it applies to desert soils. And finally, I have a little bit of advice, since I get a chance to philosophize, I'm going to use it. A little bit of advice on collaboration and publishing for our younger researchers. So first, engineering biomass. So where am I? So the US has 4 deserts, and New Mexico State University is located in a valley called the Mesilla Valley in the state of New Mexico, which is about right here. And we are on the edge of the Chihuahuan Desert. Now, some of you who have worked with engineers before will recognize this. For those who have not worked with engineers, let me give you a cheat sheet of understanding engineers. So what about us? Well, first of all, we like to measure everything. And once we measure everything, we try to model everything. If we can't put an equation to it, we get nervous. The reason we like to model everything is we are obsessed with the Goldilocks problem. Now, some of you may know the story of Goldilocks. It's a little girl. She goes to the house of 3 bears. And I don't know why she does this. Don't ask. It's a children's story. And she tries to sleep in beds and sit in chairs and eat porridge. And one bed is too small, one bed is too big, and one bed is just right. Hard and soft. One chair is too small, one's too big, just right. One porridge is too cold, one porridge is too hot, one porridge is just right. The reason engineers love to measure things is we want to make everything just right. So we put numbers on everything. Other things about us, we obsess about safety. If there is personal protective equipment, we like it. But we are not just theorists, we're very practical people. And in American English, there is a statement about practical people, is that you can fix almost everything with WD-40 or duct tape, lubricant or adhesive. One of the two will do the job. So this is engineers. Now, if I want to engineer co-products, this is the chart I always keep in mind. There is always a trade-off between how much product is available and how much that product is worth. Now, where do we want to be? We'd like to be over here. The world does not work that way. We have to make a choice. And so whenever my group is given a new material, we decide, what should I make out of this material? And where should I start? I don't start down here on solid fuels. You can burn anything, including aluminum, I learned earlier. You can burn anything. We want to start up here. And so we look at, can we get any medicines, cosmetics, spices, foods? Okay, if not those, maybe feed, clothing, fine chemicals, adhesives. All right, maybe not. Okay, paper, rubber, fertilizer. And whatever is left at the very end, that is our solid fuels. Okay, so this is how our process works. All right, so let's get some examples. So insect repellents from Wayuli resin. This is one of several projects done by the US Department of Agriculture over the last 15 years on how to make biofuels plus other things in different areas of the country. And so they have different types of lumber and timber and grasses and willow and a nice little oil seed called carinata. And then in the Southwest, we have this one. And this project was the Sustainable Bioeconomy for Arid Regions, or SBAR for short. And it focused on 2 crops that were suitable for arid regions, Wayuli and guar. I'm not going to talk about guar, but I will tell you about Wayuli. So what is Wayuli? Wayuli is this. It is a shrub. It grows about this high. It has woody stems, yellow flowers, and it smells wonderful. You will see later that there are many things in my lab that smell terrible. Wayuli is the one that smells nice. And this project is led by the University of Arizona. And this is some of the people involved. And what we're trying to do with Wayuli is develop several co-products. So this is the word Wayuli. It does not look like it sounds like Wayuli. It looks like guayule. Okay, Wayuli is how you say it, or Parthenium argentatum. And it's used as a rubber plant. It produces high quality natural rubber, or polyisoprene for the chemists present, in its stems. And the way it's processed is you take the shrub, you cut it off, you grind up the woody material, you extract it with a solvent, you precipitate the hard rubber from the solvent, and then you use the products that are left over. So this is what the rubber looks like. And these are the process engineers at Bridgestone Tire Company. Some of you may have heard of Bridgestone. And this is their processing facility in Arizona. And this is how much rubber they made. Okay, this is pretty good. All right, they sent that to their processing facility. That is not what I care about. What I care about is everything else. So this represents about 5% of the plant. This big picture is the bagasse. This is the woody shrub material, looks like ground up wood. And then these barrels back here, which is about 10 or 15% of the plant, is a resin. And so my group's job is to deal with the bagasse and the resin. So here's the shrub. You grind it up, you do an oil extraction to form a micella, a mixture of compounds. You precipitate the hard rubber, and then you boil off the solvent. And this is what my group gets handed. They get the bagasse and they get the resin. And so we looked at the bagasse for advanced biofuels. I'll give you the end of the story. It's a lot like wood. It burns just fine. And then the harder part was the resin. We wanted to find value-added chemicals from this resin. So first thing, what's in it? How many of you have taken organic chemistry? Okay, this will be, for those who have not taken organic chemistry, my sincerest apologies. So here's what's in it. You start with low molecular weight rubber. So this is the rubber molecules, the polyisoprenes that were too small to precipitate. Then you have some plant sterols, you have some fatty acids and triglycerides. Up top, you have alpha-pinene, these monoterpenes. If you like essential oils, this is why it smells so nice. That's this compound. We have oxygenated terpenes. And then we have two sets of compounds that are unique to Wayuli. This is the only plant that makes them. The Wayulins, which are sesquiterpenes, and the argentatins. And so we wanted to see, is there something, these chemicals people know how to use, these chemicals people know how to use. We wanted to see, can we use these unique compounds? So we made our chart, and Mostafa, one of my recently finished PhD students, did a literature review of all the ways people have used Wayuli resin. And there's many things. And we noticed there was this one where we want to be, high value, high volume, and that is pesticides. And so we said, let's try to make bio-derived pesticides out of Wayuli resin. And we did some things that chemical engineers never like to do. We worked with living things. And we started with our favorite, the cockroach. So what did we do? We first wanted to separate it into fractions, because if you can separate it into fractions, you can sell one fraction for one thing and one fraction for another. And so this is a vacuum distillation. And so we separated it into fractions. We tested the toxicity and avoidance of the fractions. We picked our favorites, and then we used those against other species. So the mosquito trials just finished, but I don't have the data yet. And then we have to calculate the economics. So how does this work with cockroaches? For those who don't know cockroaches, they like to be under shelters. They like to live in tents. And so we have our control here, and the tent was only treated with acetone. That was our control solvent for dissolving the compounds. And we have these video monitoring systems that track the path of the cockroaches. And so we watch where the cockroach goes. And a cockroach will first try to get out of a container, or if they can't get out of a container, they will hang out under the shelter. This is what cockroaches do. I never knew this before, but people study this. And so this is what the control looks like. Now for our positive control, we use Java citronella oil, which we know cockroaches don't like, and we put that on the tent. And so the cockroaches, instead of going under the tent where they'd usually like to be, they got as far away from the tent as they could because they don't like the smell. So this was our positive control. Now for some of our Waiuli resin, we saw this. The cockroaches stayed as far away from the tent as they could. And they did this over and over and over again, which means there is something in Waiuli resin they really don't like. And so we studied the fractions that they didn't like and are currently trying to publish this work. But this was very exciting to pesticide companies because this is a plant-based material, should have a low toxicity for humans and animals, and it will keep the cockroaches away. What was more exciting is we let one set of samples dry for a week because people are like, oh, it's just volatile compounds. They'll all evaporate, which is what happens to most bio-based repellents. After 1 week, it still worked. The cockroaches still stayed away. So we were very excited about that. So this is one example of a co-product from a plant. Now we have hydrothermal liquefaction of algae, sludge, and food waste. This did not smell good. So what do I do? So as a chemical engineer, I'm trained in thermochemical processing, and we have several sets. We have dry and we have wet. And so I specialize in slow pyrolysis and hydrothermal liquefaction. This is moderate temperatures, high pressures. This is your kitchen pressure cooker on steroids. That's what it does. And we do subcritical, and this makes a biocrude oil. So what happened here? So this was the idea. This was sponsored by our National Science Foundation. And this was a project to find energy recovery from wastewater. And so the wastewater comes in, it goes through a primary treatment, that's just a filter. And then it gets fed to a mixotrophic algae. Mixotrophic algae can grow on sunlight or grow on carbon that's present. And they will take all the carbon and nitrogen and phosphorus and incorporate it into their little bodies. And then clean water will come out. The algae we use is amazing. It does this in 3 days. Then we take the algae, we put it through hydrothermal liquefaction, and we get our products. Now, this was the first design. By the way, this didn't work. And the problem was the aqueous phase. So one of our phases is a watery phase. And we thought, oh, water with nutrients, we feed it back to the algae. Don't do that. It kills the algae very quickly. But so we had to work on this. But then we saw there'll be a char fraction for fertilizers. And the product of the algae is a crude oil that can be refined and separated for liquid fuels, which was the goal to make biofuels for transportation. As I said, this was the original plan. This didn't work. But here's ideas what it looks like. So these are our very high-tech photobioreactors. They're plastic bags with a stirrer. And this is at our wastewater treatment plant. You can see one of the students taking samples. This is our pressure cooker reactor. It's about 2 liters. And here's what happens. We get a bag of green, we cook it, and we get a mixture of products. And then we separate it, ultimately getting the biocrude oil. So that's what the process looks like. In the end, so we're wrapping up this project, we found that we don't make just one phase. We don't just make oils, we make several products. So we have our wet biomass. There are off gases. This is your biofuel. Okay, and this is not very much. It's like 10 or 15%, but we have some. We get the water phase is rich in nitrogen. We learned do not feed it to the algae, instead make it into ammonium sulfate and sell that as a nitrogen fertilizer. Then you take the char, you leach it with a base, a hydroxide, and then you precipitate struvite and calcium phosphate. So you have a slow release phosphorus fertilizer, and then you have a residual biochar that is carbon. And so out of our algae, we don't get one product, we get many. But the goal was we want to use all of it for the highest value we can. Then we tried the same thing with food waste. If you're about to eat lunch, I apologize. This was taken from one of our campus cafeterias, and this was Hengame's work. She made a food waste slurry that went into our pressure cooker. And like before, you have a char, an oil, and an aqueous phase. And her PhD was finding a use for each of these products. And so the first one, this has been published already. She characterized and worked on upgrading the bio oil. We're about to publish, I hope. This one, we use the char to remove heavy metals from water. And it turns out that if you take the char and process it with another waste, red mud from mining, you can get a char that will absorb lead, copper, and nitrate. And so we're working on that publication now. And then for the aqueous phase, we know don't feed it to algae. We have to feed it to something more robust. And so we put it in compost. And it turns out that compost can handle the compounds that are in the aqueous phase. And so this last year, she demonstrated you could grow compost or make good compost using the watery phase and the nitrogen from the food waste. So again, primary product, the oil, but also we don't let anything go to waste. We try to use all of it. All right, so speaking of, let's talk about hemp. First of all, I am required to give you the definition. So the definition is cannabis sativa. In the US, I say cannabis and people giggle because it sounds like they're doing something wrong. This is not the weed you were looking for. Okay, the stuff we work with has to have less than 3% of the THC. And these are where hemp is currently cultivated. Some countries use it for multiple products. The US primarily makes hemp for cannabinoids. Now, how many of you have worked with hemp before? I know at least one of you, okay? So something you might not have known about hemp. By the way, this is Hannah. This is the PhD student working on this project. Cannabinoid hemp looks like this. It's big and bushy because cannabinoid hemp, you want lots and lots of flowers. That is not the same as fiber hemp. This is me by fiber hemp. And I'm pretty tall, but you can see that this is like 3 or 4 meters high. It is long and stick-like and looks like bamboo because you want long fibers in the stem. And this is grain hemp. Kind of tall, not very bushy, a lot of straight, but lots and lots of seeds. And so if you've never seen hemp varieties, I want you to know that there are cannabinoid types, lots of flowers. There are fiber types, really tall and skinny. And there are grain types, lots of seeds. And we tried growing different types of hemp in our part of New Mexico. Now that caused a problem because of this. So photoperiodism. What this word means is that the amount of sunlight or dark changes what a plant does. So in places where there are very long days, like high latitudes, like Lithuania, there are some plants that will bloom and other plants that will not. And other times there are short day plants where the days are shorter, the nights are longer, and that causes them to bloom. And then they did experiments with, flashing lights on the plants in the middle of the night to confuse them. Most hemp was bred for regions like Lithuania, where there are very long days in the summer and very short nights. The problem with New Mexico is we're at a lower latitude. And so our hemp thought, oh, the nights are short, or the days are getting shorter. It must be autumn. It must be time to bloom and die. So what happened to our hemp? Premature flowering. Our hemp started flowering at 17 days old. Hemp is supposed to be like this tall. It got to this tall, said, oh, it's autumn, it's fall, it's time to flower, and it's this tall. This is not good for any kind of hemp. So that's what happened in New Mexico, and you can see some pictures. And so after 2 years of field trials, we came to an important conclusion. We should stop trying to grow fiber and grain hemp outside in New Mexico. It doesn't work. Instead, we should let our farmers cultivate cannabinoid hemp, so the bushy hemp, inside greenhouses. It gets pampered. Okay, so that's what we ended up learning. I learned a lot about plants in this study. So what is Hannah going to do instead? Because her plan had been variety trials for hemp. Now she has to do something else. What we discovered is that in the hemp industry in New Mexico, there is a lot of waste, because what do the processors do? They take off what? The flower, and that leaves all the stems behind. And so what she's been doing is taking the stems. So this is not fiber hemp. This is bushy hemp. This is cannabinoid hemp. She's digesting it down to sugars and then trying to produce an important biochemical. This is succinic acid. This is a platform chemical to make other high value chemicals. So she's trying to take the hemp waste and turn it into succinic acid. So I hope to have more results from that this fall. So this is an example of utilizing hemp. First of all, what kind of plant? What should be the primary product? In this case, the primary product are the cannabinoids, which is CBD and THC, by the way. We're trying to make a secondary product is high value chemicals. All right, last example, I'm going to talk about biochar in desert soils. I was very grateful to our first speaker for talking about the opposite of what I'm going to talk about. So in Poland and Lithuania, you have sandy soils, you have lots of water, and you have acidic soils. The desert is the exact opposite. So these are arid lands, and about 1/3 of the world's total land area is arid. And if you didn't know this about the US, most of our Western states are dry. New Mexico is particularly dry. And this holds about 1/6 of the world's population. Now, most biochar research in the past wasn't done on arid soils. It was done on soils like the soils here. So we have a lot to learn about what could happen. Now, why is this a problem? In desert soils, there are two things that are out of balance. We have precipitation, which is not much. And we have evapotranspiration. This is how much the plants take up water from the soil and have it evaporate from their leaves. It gets really hot in New Mexico, and so the plants do a lot of evapotranspiration, but we don't get much precipitation. That means there is always an imbalance between the water going into the soil and the water coming out of it. And this leads to a lot of salt problems, because salts will dissolve in the topsoil, but before they get washed away, the water evaporates. And so what do we worry about? Well, I wish I worried about soil acidity, and I wish I worried about water erosion. No, here's what I worry about. I worry about soil salinity. I worry about my soil being alkaline. Okay, many of our soils have pHs greater than 7, some as high as 8, 8.5. We also have to worry about sodic soils where there's too much sodium. Now, how does that relate to biochars? So biochars are chars made from biomass that you put on the soil. And we found some really good things, really exciting things about biochar in desert soils. First of all, it leaches the salts below the root zone. It allows the water to move easier. It makes good ions available, calcium, magnesium, potassium, and it causes less problems with sodium. It increases plant available water. If you are a farmer who irrigates, the amount of irrigation water you put down is one of our biggest expenses after seeds in this area. And so what we found with biochar is that if you put down biochar, you get to use less irrigation and your crops still survive. And anytime you can use just a little bit less water in a desert is a very big thing. It helps prevent soil compaction. And even in soils that are saline, the plants tend to grow better when there's biochar present. So we were really excited by some of these things. There are some potential problems though. And I'm an engineer, so I get more excited about the problems than the victories. In our chars, we have high ash content, and that causes an increase in soil pH. Now, if I have an acidic soil, this is a good thing. But if I have an alkaline soil, this makes an alkaline soil worse. Some of our chars have high sodium content, which could be a problem on a desert soil. And some of our chars have a high amount of salt in general, which could also be a problem. And so we have to warn farmers to pay attention to pH and salinity. So here's some work that's going on. This is at one of our research farms near NMSU, and this is a pile of pecan wood. We are one of the largest pecan producers in the US. We also grow chilies and onions, by the way. And if you think your chilies are hot, you should try ours. Okay, so this is pecan wood from the tree prunings, and this is one of our kilns. It's called a ring of fire kiln. It's a big metal circle. And we made char as a demonstration for local farmers. And this is our farm manager cooling down the char after it was done. And so this char is being used on a study that mixes compost, biochar, cover crops, and reduced tillage. We're in the second year of a 10-year study on soil health. In soil health, cover crops are usually a good thing. In the desert, we have to be careful with cover crops because there's always a danger that our cover crop will use all the water that the regular crop needed. And so this can be really difficult. The study that Ayaz helped with was biochar interactions with heavy metals and micronutrients. Biochar is a good absorbent. We're worried that it'll absorb the heavy metals and all of the iron that the plant needed. And so we're working on this one right now. In the future, we have two things we found we need to study. People have found that biochar lowers the emissions from cattle farms. What we're trying to determine is, should we put the char on the soil, or should we feed it to the cow and let the cow put it on the soil? This is an interesting question because in the US, there are very special rules about what you can feed to cows. And so we're trying to answer this question next. We also found that biochar as a good absorbent can occasionally absorb all of your pre-emergence herbicides that you put down. So you put down your herbicide, you wait for your plants to grow, and the char absorbs all the herbicide. So we're trying to understand the best practices for biochar and herbicides. All right, so that was my last example. Now I have a little bit of advice for the young researchers here. These are some things that I have learned as in my 10 years as a faculty member. The first one is on collaboration. People ask me, what do you do? And I say, I do all of that. So they pay me to teach chemical engineering, but you can't be a good engineer without good analysis. By the way, if you have a chance to take analytical chemistry, do it. It's a very boring class, but it's very helpful. I do a little bit of environmental engineering. We clean up heavy metals. I'm part soil scientist. I'm not good at growing plants, but I'm good at studying plants. We do a little food science. And then I also do some research in education. And people ask me, how do you find these wonderful collaborations across so many disciplines? And the strategy is a Venn diagram. So when I first arrived at NMSU, the first thing I did is I went over to our College of Agriculture and I knocked on doors and said, hi, I'm new. What do you do? And they talked about what they did, and I talked about what I did. And we tried to find the area where our Venn diagrams overlapped. And my advice to you is, don't talk to the people who do research close to your area. It's too easy. Talk to people who do research that is far away from your area, because the small place where you overlap is an area of research not many people will do. This is how I get some of my most creative ideas. So, chemical engineer, cockroach behavioral specialist. Hey, it works, okay? But if you want to write proposals that no one else is writing, find the people whose disciplines are very different than yours and learn to work together on important problems. So that's my advice on collaboration. Oh, also, how many of you are shy? You don't like to meet new people? Okay, have a beer and go meet them anyway. It's worth it. All right, perspectives on publishing. So for the last 3 years, I've worked as an associate editor for renewable and sustainable energy reviews. And I've learned a lot about publishing. And I wanted to share some of that advice because all of you will have to write at least one paper. Okay, PhD students, probably more than that. And people ask me, how do you write? I start writing and I get stuck. That's because most people write in the wrong order. How do you read a paper? What do you read first? Abstract, introductions, methods, results. This is not how you write a paper. You write a paper from the inside out. And so you start with the methods. Why? It's easy to write because this is what you're doing. If you do something in the laboratory, write it down. Hey, I got 2 sentences in my paper already done and it's the first day. Okay, you start with your methods because this is easiest. Then anytime you do something, you see something. So you write, what did I see? What did I do? What did I see? What did I do? What did I see? What did I do? What did I see? This is also easy to write. Then and only then, so do this first. Then you write the next 2 pieces together. You write the introduction. What does my reader need to know to understand what I did? That's it. You don't have to give your entire dissertation, just only what they need to know to understand your methods. Then discussion. What did you see compared to what did other people see? And why does it matter? Much easier to write when you have results. Then you write your conclusions. And then, only then, do you write your abstract. Do not write your abstract first because you will only have to rewrite it. Okay, but if you get stuck on writing, start with these. They're much easier. All right, other things. People ask me, how do I write a paper to get accepted? So these are my main reasons I desk reject papers, and I desk reject a lot, and how to deal with it. One of the big things is novelty. Now, this does not mean that your study is not new. Most people have the problem because they do a bad job of telling me why their study is new. They talk about the general things. So I work on energy reviews. If I have to read one more introduction about climate change and why it's important, I'm going to scream. Don't start there. Start with why. Go right to why your study is special. Be specific. Do it early and do it often. When you read hundreds of new manuscripts every year, they start to look the same. If you want to get your article published, don't make it look like everyone else's. Be specific. All right, scope and author guidelines. The journals write these for a reason. Read them. Please read them. First, halfway through, and before you submit. Your editor's blood pressure will thank you. Then, language. Now, I know that English is an incredibly difficult language to learn. I used to teach it. It's frustrating. I'm not talking about just general English. What I mean is scientific English. And so what I want you to remember is be precise and be concise. So precise is say exactly what you mean. If you mean to say very large, say very large. Do not say huge. Do not say massive. These are words that are appropriate for social conversation. These are too imprecise for science. Say exactly what you mean in a way that an engineer will understand, measurable. Okay, be precise. Then concise. Do not write the way you talk. When we talk, we add transition words, we add colorful language. Don't do that. Short, choppy sentences are your friends. Precise and concise. And finally, give some insight. A lot of students are afraid of making an argument in their paper. The argument is what makes it interesting to read. So have an argument, but don't just have an argument. Justify that argument. Give your readers some insight. All right, I've talked too long. This is my contact information if you'd like to reach me. One of my other favorite jobs is I run our brewery engineering program. So I also am happy to talk about beers. And for the minute that I have left, time for questions.
Yeah.
So thank you.
So now it's time for the questions. Any questions? No?
Yes, I have.
Yes, please.
Just the background is in plant biotechnology and molecular biology. So just like I'm curious about one thing you mentioned in your slide that hemp production was stopped because it was not suitable according to your like environmental quality. So my question is that your group is working on multidisciplinary things like many things. So you never tried like collaborating with molecular biologists or plant biotechnologists so that they can transform the hemp so it can be grown in your locality or your like environment, because there are many techniques they can like make like varieties that can grow in different environments in different like conditions. Thank you very much.
So yes, I do have a couple of colleagues who are molecular biologists. We put in a proposal earlier this year to do that exact thing, and they said no. So it was something that I think needs to happen, because hemp is one of those crops that should be grown, I think, around the world. And if you saw my chart before, almost everything was in the northern latitudes. And so there are breeds that are suitable for lower latitudes. The problem with regulations in the States is those varieties tend to go hot. They have too much THC. And so if you want to be that molecular biologist that breeds low THC hemp for lower latitudes, let me know when you have stuff you need tested, because we would love that.
Thank you very much for the nice presentation. I really enjoyed it. Please, I just have 2 questions, please. The first one is actually on the pesticide. Is in 2 foods. The first one is on the let me say about pesticides. I have a background in microbiology. There are cockroaches based on the area where I come from, Africa. There are a lot of cockroaches. And result of your study I have mentioned, they repel. From where I come from, instead of repelling, we kill. How have you done any kind of research or results on that instead of repelling? As farmers or from developing countries, we tend to look at the toxicity, killing rather than repelling. If they repel, we go to another place. So we're not really controlling. And yes, we're just preventing. So I would prefer the control to the prevention. So has there been anything done as regards that? Then the second question would be as regards climate change. New Mexico, arid region in US. Has there been any kind of I know you have a lot of issues with moisture, soil moisture. Have you really done anything on these effects? Because how do you think to improve the soil moisture of the soil from all these problems in the context of climate change and organic matter? Because I can see you do a lot of other things, but most, how do we retain the water? How do we find the balance between the transpiration and the evaporation? Thank you.
So 2 very good questions. All of the people in New Mexico would agree with your sentiment about cockroaches. They love to kill them. We started with repellency as a preliminary study to see if it was worth studying at all. Because if it doesn't repel, it's definitely not going to kill. The follow-on studies, and we're working on proposals for this, is understanding the level of toxicity, if anything, and then how it changes with formulation. So that is coming next. We see it also repels mosquitoes, but we think by a different mechanism. And so we are studying that. But yes, I tell my children, you can't hate anything, but you can hate cockroaches and mosquitoes. Kill them on site. With regard to soil moisture, there are many efforts and many strategies. With crops like Wayuli, the strategy is use a crop that needs less water and that can wait for water. So many plants, if they don't get enough water at a certain time, they'll dehydrate and die. Wayuli, like many desert plants, if there is no water, it just sits there and sits there. It does not grow, but it does not die. And so there is a lot of work in the southwestern US on alternative crops, not just that are suitable, but also that can make these high value products, because the farmers still have to make money but they need crops that are suitable for the amount of water that's available. And so there's a lot of work going on, and alternative crops is just one option.
We have more questions? Yeah.
Thank you for your presentation. So since like hemp and biochar are your new research, about your long-term programs, which long-term programs do you have? What plans and management systems do you use?
What long-term
Long-term programs, experiments, long-term.
experiments? So as a chemical engineer, they do not let me do field studies. I only get to work with the people who do. And believe me, you don't want me growing a plant. I'm really good with dead plants. So there is the 10-year soil health study, which is the cover crops, biochar, reduced tillage. There's that study going on. We have a proposal on a study to take oil seed stems, so like canola, and put it on soils and track the carbon fluxes over 7 years. And so if that one is funded, that will start next year. For hemp, we have stopped most of our research because most of it is not happening in the field. Most is happening in the greenhouse. Almost all of the New Mexico cannabis production is for recreational. It's for weed, to be specific, and which is something the university is not allowed to work with. And so we do some advising on, we can help the industry deal with their waste, but we can't really be involved in their greenhouse production because of the THC and the legal rules. There's a project I did not talk about, which is our work with coal fly ash and extraction of rare earth elements using food grade acids. So I think my future will have a lot of work in uranium and rare earth lanthanides. I didn't talk about that here, but I was super excited by the nuclear presentations earlier. So does that answer your question? But in general, for me, anytime there is a waste from a plant, I'm interested in figuring out how to use it.
Thank you for your incredible presentation. I wanted to ask about aquaculture in New Mexico.
Mm-hmm.
What's the size of aquaculture waste in New Mexico, and have you conducted any experiments on aquaculture waste management?
So there is a lot of agricultural waste, but you mean aquaculture? Aquaculture. Okay. There was a group that was growing shrimp in New Mexico, which is very strange because we're about 2,000 kilometers from the ocean. It has not taken off much. So there are some people that will build the controlled environments with recycled water through plants and fish systems. There is some, but not much. Is that your question?
Yeah. Have you conducted any experiments about management of aquaculture waste?
Not yet.
No. Yes.
More questions? No, then we have a present. Actually, I wrote one question, but then you showed the slide where our PhD student Muhammad Ayas came and did that result. So my question was just thank you so much for a very interesting presentation. And now we should have our last section, but I want to ask you to make 10 minutes short break and then come back here and then continue with the last section. Okay? Thank you.